This first part of section 9.2 is going to be using what we learned in 9.1, the significance test or hypothesis testing, and we're going to use it with population proportions. All right, so we're going to revisit that example we were talking about where the free throw shooter claims to have an 80% free throw rate or proportion. So the person claims that they can make 80% of their free throws. All right, and so what we do is we send that person out onto a basketball court and have them throw 50 baskets. And let's assume that this person, she makes 32 of her 50 baskets. All right, that doesn't sound too bad, but when we look at it as a proportion, that means that our p hat, that her p hat, is going to be only 64%. So 64% seems to be kind of low, right? Much lower than what she claims. She claims that her true or population free throw proportion was 80%. And then in a sample of 50, she only threw 64%. All right, so does the sample statistic, the p hat of only 64%, does that give us convincing evidence or provide convincing evidence against her claim that she's an 80% free throw shooter? All right, so if we look at this as a significance test, we want to start with our hypotheses, and so our null and alternative hypotheses. Now, we just already discussed her p hat. So we know that her p hat is 64%. So it would be sort of cheating if we waited until we looked at that result of the sample, the 64%, before we decided what the alternative hypothesis would be. All right. If we really don't know the person and we don't think that they're a braggart, we would just say, well, we don't know if 80% is correct. We don't have anything that indicates that her 80% should be high or should be low. In which case, we would probably say P as our alternative. We would say P is just not equal to 80%. But here, I think if we were remembering what we were talking about in the last section, we were saying, well, we think she's a braggart. We think that she's boastful. And so we think her true proportion is going to be lower. Okay, so we set up those hypotheses before we send her out to do her p hat. Okay, remember that the p is the population or actual proportion or true proportion of free throws that she makes in the long run. Okay. All right. So in chapter 8, when we were doing confidence intervals, we had a couple of conditions we had to check. And so those same, more or less, those same three conditions are going to apply here. In 8.2, we did proportions, in confidence intervals proportions. And so the same three conditions apply for significance tests for proportions. All right, so random, we have to make sure that our data came from a randomized sample or a randomized experiment. Again, we'll get into more randomized experiments in chapter 10. All right, 10%, again, we didn't sample more than 10%. And then the third one is the large count. Now, the large count's slightly different. We're not using p hat because remember, we're assuming, until we know otherwise, we're assuming that the null hypothesis is true, that the p naught or the hypothesized p-value in the null hypothesis is true. So that's why it kind of makes sense that when we're checking our large count conditions that we're using n times p naught. So for us, that would be n, sample size of 50, times the 0.8, the hypothesized value, and then n times 0.2, 1 minus that. Okay. All right, so again, we're assuming the null hypothesis is true, that her true free throw proportion rate is 80%. Okay. Now, what we want to think about is our sampling distribution. So every time if we sent her out to shoot 50 baskets a whole bunch of times, then all of those resulting p hats would fall on a sampling distribution. And we're going to assume that that sampling distribution is centered on the hypothesized p-value 80%. Okay, so we're going to assume that the null hypothesis is true, and so we're going to also assume that our sampling distribution is centered on our 80. Remember that the mean of the sampling distribution of p hat is going to be equal to p, but in this case, we're assuming the null hypothesis is true. So p naught is what the true p is, or 80%. Okay, and so what we're going to do is calculate, just kind of like what we did in chapter 7. We're going to take it to a little bit more higher level, but in chapter 7 we said, what's the probability that we would be at a certain value or one more extreme? And so we're going to do that. We're going to say, assuming the null hypothesis is true and the sampling distribution is centered on that hypothesized p value, what's the probability that we would get a p hat as extreme or more extreme than the one we got? All right. And so when we calculate our standard deviation of the sampling distribution of p hat, we are going to use, again, p naught and 1 minus p naught, because we're assuming that those are true. So we don't use, when we did confidence intervals, we didn't have any other choice. We used p hats when we did this calculation. The standard error in the confidence interval and as part of the margin of error. But here we're going to, again, assume the null hypothesis is true, so it makes sense that we're using p naughts, p subscript 0, p naughts, in the calculation of the standard deviation of the sampling distribution of p hat. All right, so some things we need to know, some principles that apply to the hypothesis test. So a test compares a statistic calculated from the sample data to the value of the parameter stated in the null hypothesis. So in our case, we are comparing our p hat of 64% that she got from her 50 attempts. All right, the p hat was 64%. Comparing that to the 80% she claims to be. All right, values of the statistic far from that null hypothesis value in the direction of the specified alternative hypothesis are going to give us evidence against it. So the further away, it kind of makes sense if you think about it, the further away the p hat is from the hypothesized value, the less likely the hypothesized value is actually true. And we're going to figure out, how far away it should be. Really, we're going to look at it like, what's the probability that we would get that result, or one more extreme. And that's really what we're going to look at here. All right, and we'll use what we call the test statistic. It's the z-score, basically, in this case. So the test statistic, it's the statistic minus the parameter divided by the standard deviation of the statistic. So it's the p hat minus the hypothesized true p-value, we're assuming is true, divided by the standard deviation of the sampling distribution that we just calculated a couple slides ago. All right. So what would we get when we standardize, or when we find that test statistic? So z is going to be 0.64 minus 0.8 divided by 0.0566, which was the standard deviation of the statistic. And that gives us at negative 2.83. So that means our test statistic, right, our p hat, is almost 3 standard deviations below the mean. And what we want to ask ourselves is, what's the probability, and now these are drawn pretty much to scale here so you can see, what's the probability that we would be as low as 64%, right? with our p hat as low or lower, and that's this little shaded region up here. So pretty small, about 0.2%. So a fifth of 1%, pretty small. Now the first graph here, A, shows the shaded region and our p hat value on a normal curve. And then graph B, is showing that same value, but on a Z curve, so a standardized normal curve. So instead of listing the value on the bottom as 0.64 for the p hat, they're putting down the Z value, the test statistic, as we call it. But notice this area is the same as the one up above, and we would expect that to be. Okay, so that shaded region is the p-value that we talked about last section. So the p-value is the probability that we would be as low, with our p hat would be as low or lower than the one we got, assuming the null hypothesis is true. So assuming that she actually is an 80% free throw shooter, the probability that she would have a p hat at 64%, or one more extreme than that, lower, is so low that means it's very unlikely she would have done as badly or worse than she did if she was an actual free throw shooter of 80%. So that shows evidence against her claim of being an 80% free throw shooter. Okay, so if H naught is true and the player is 80% free throw, makes 80% of their free throws, then that means that there's only 2 in 1,000 chance that she would have done as badly as she did or worse. So that means she probably is not an 80% free throw shooter. Okay, what's really going on is, since that probability of this happening is so low, just by chance, it's probably not happening by chance. And it's possible that she just had a really bad 50 throws, right? I mean, it's possible, but very unlikely. And so really what that says is, when we have a small p-value, we are going to reject the null hypothesis. We're going to reject her 80% free throw shooter, being a free throw shooter of 80%, and say that it's probably less than that. All right, so we're going to do some examples of some four-step processes, and let's discuss what it takes to do those four-step processes. So we're sort of introducing our third inference procedure. We had 2 inference procedures last chapter for the confidence intervals, and this is the first one for significance testing. So our third inference procedure. So this is a one sample, because again, we're going to go in the next chapter, we're going to take more than one sample. We'll take a sample from 2 different populations, but here we have one sample. The sampling distribution, assuming the conditions are met, is normal, so we call it a Z. And we're not creating a confidence interval. And here we're testing a hypothesis. So it's a test. And then what is the parameter that we're testing something about? It's proportion. So that's how we get the name for this inference procedure, or one sample Z test for P. All right, so the first thing we want to state, we do in the state, is we want to make our hypotheses. So H naught and HA, the null and alternative hypotheses. We want to say what significance level we're using. And then those symbols, in this section, it's going to be P is equal to, and then P is not equal to, or P is less than, P is greater than. Those P values, the parameters, you have to explain what those are in context. So really 3 components to the state. All right, the plan. We want to state the inference procedure, one sample Z test for P, and then we want to test our 3 conditions. All right, so make sure we're looking at those 3 conditions, and then the do. All right, so there are some components that we need to include at the do this time. So we want to calculate our test statistic. What is the test statistic, or the Z value? We want to draw a normal curve labeled and with shading. And then we want to calculate our p-value. So 3 things we have to include. We can do this by hand. We can use our calculator for these things, but we have to include the test statistic, the p-value, and a labeled shaded normal curve. And then finally, the conclusion. The conclusion has three components. We want to compare the p-value we got. That's that shaded region, right? It's the probability that we would be as extreme or more extreme than the statistic we got, assuming the null hypothesis is true. So we compare our p-value to the alpha. That's the significance level up above, what we talked about here, right? We claim what the significance level is up here, and then we compare that to our p-value down here. All right, then we decide whether we're going to reject or fail to reject H naught. And then finally, we discuss whether there is convincing evidence or not convincing evidence for HA. Now, the H naught, we just say H naught. We actually use that, that term, H subscript 0. But when we talk in the third part here, HA, we don't say HA. What we say is what HA is in context and in words. All right, so that's kind of a little difference between those two components in the conclusion. All right, when the conditions are met, and we check our three conditions, right? The random, the 10%, and the large count conditions. Remember that the large count is using P naughts in there. We know that the mean of the sampling distribution is going to be equal to the hypothesized p-value, and that this standard deviation of the sampling distribution is going to be p naught times 1 minus p naught over n, and then the square root of all that. All right, the z statistic has approximate normal distribution, assuming the null hypothesis H naught is true. P-values come from the normal distribution. So it's the shaded region on that normal distribution. It's the shaded region from our statistic and further down into the tail. All right, so we choose an SRS of size n from a large population. We have a null hypothesis that says something like p is equal to some value. So p naught here is going to be like a number, not a variable. So p equals a number, and then we're going to compute the test statistic. Now the alternative is either going to be that p is greater than that one number, that value, whatever p naught is, that it's less than it, or that it's not equal to it. So remember that the p-values that we calculate correspond to the shaded region. All right, so if we have an inclination as to we think the true p-value is going to be higher than this, and then we're going to go take a sample and see where the p-hat is, right? So if we have an inclination, we're going to use a one-sided test, which is p is greater than the value, p is less than the value. Okay, if we don't have any inclination as to what direction we think the true proportion is, like, okay, we have a set value, but we suspect that maybe it might be wrong, but we're not sure what direction, then we use a two-sided test. Okay, now notice the p-value in a two-sided test is twice as large because we have shaded regions in both tails. So it's actually harder to reject the null hypothesis. So if you think the null hypothesis is wrong, what we don't do is we just say, well, let's just run a two-sided test. If we think it's lower, if we think like, oh, they claim it to be 80, but we know that Susan is a braggart, we're not going to just do a two-sided test, because it would be harder to prove, or not prove, but harder to show evidence against her claim because our p-value is twice as large. So we might go over that threshold of alpha. All right. So if we know a direction, if we have a suspicion of a direction, we're going to use it. And remember, it's cheating to send her out and have her take those 50 shots first before we decide on the direction of the alternative hypothesis. We got to come up with that first. If we don't have an inclination as to what direction, then we just have to use a two-sided test. All right, let's go through an example. Drug company claims that their new drug works for 20% of those with a particular disease, and the FDA thinks that the true proportion is less. Okay, so use that information. You have on your paper, the rest of the question sitting there, but I specifically hid the rest of the question because I don't want us to think about looking at the statistic to help us come up with the alternative hypotheses. So come up with the null alternative hypothesis, the alpha level, and also say what P is in context. All right, so the test that we're going to perform, we will perform a test, a significance test, hypothesis test, of the following hypotheses. Null hypothesis, P equals 20%. Alternative, P is less than 20%. We're going to use an alpha of 0.05, and we're going to say where P is the true proportion of drug takers who are cured or, that no longer have the disease after taking the medicine. Okay. And again, if we look up here, we can see they give us the statistic, right? 300 people have the disease, and 54 of them are cured. We don't want to be looking at that to help us decide that the alternative hypothesis should be less than. Okay, we have to come up with that not from the statistic, but from what the FDA, the Food and Drug Administration, has come up with, what they think is going on here. And so that is what we use to come up with our alternative. Okay, so now let's do the state. So we want to say, what is our inference procedure? Well, it's right there at the top of the slide, a one sample Z test for proportion if conditions are met. And think about the three conditions: random, 10%, large count. All right, so we're going to do a one sample Z test for proportions. They selected a random sample, an SRS. We can assume that we have to assume that there are more than 3,000 people with this disease. The large count is N times P naught and N times 1 minus P naught. Remember, we're not doing the P hats there. We're doing the P naughts because we're assuming the P naught is true until we know otherwise. All right, so both of those are greater than 10. So the sampling distribution of P hat is approximately normal. All right, so the do. All right, so a couple things. First, we need to calculate our P hat so that we can calculate our test statistic. So our test statistic is here. Then we can either go look at a z-score table, and that would give us our p-value or our area. Don't forget, we have to have a normal curve with shading and labeling. All right, so we put down there the z, in this case, I put the z value. So the z value is negative 8.66 or 8.7. All right, I could have also put the, instead of putting a 0 in the middle here of our, instead of putting that 0, I could have put the hypothesized value of 0.2. And then I could have also put down here our P hat value. So you can either do your labeling on your normal curve as the P values or as the Z statistic. It's up to you. All right, and then the conclusion. Three components. So we compare our p-value. I usually put mine right in there. So the p-value, and then kind of in parentheses, of 0.19 is greater than our alpha of 0.05. So therefore, the p-value is not small enough. We could have gotten this result pretty frequently, 19% of the time. It's not that rare. So we would fail to reject H naught, and then we say there is not convincing evidence that less than 20% of those. So we're saying the alternative hypothesis. So we're taking what we have up here in words and saying it in that last part. So we do not have convincing evidence that less than 20% of those with the disease could be cured with the new drug. All right, let's look at another example. The New Jersey Department of Education claims that 12% of high school students will opt out of taking the PARCS exam. The Montclair PTA thinks that the proportion is actually greater. The proportion of people who are opt out is actually greater. All right, so use that information, even though you have the rest of the question in front of you on your paper. Use that information alone to come up with your null and alternative hypotheses. I would say pause the video until you get those written. Okay, so the state is that the null hypothesis is always given as an equal sign. So P is equal to 12%. Now, the PTA thinks that that number is actually greater than 12%. So that's the alternative. We suspect that the true proportion is wrong and that the true proportion is actually higher. So that's the direction of our alternative hypotheses. An alpha of 0.05, and then we have to say what the P is. The P is the true proportion of Montclair students who plan to opt out. All right, so does that same number apply to Montclair students, basically? All right, so the plan now. Again, the inference procedure and the 3 conditions. Pause the video until you get that written. All right, so the one sample Z test for proportions, an SRS was taken of Montclair students. Assume that there are at least 1,000 Montclair students because we randomly sampled 100 of them, and then check the large count. So N times P, 100 times 12. And again, remember, you're not using P hats there. You're using P naught. So it's 12 and it's 88. So both greater than 10. So the sampling distribution of P hat is approximately normal. So we can calculate our test statistic using a normal curve. So that's the whole point of showing that it's normal. We know our sampling distribution is normal and our test statistic is going to be a Z. All right, so do your calculations. Pause video until you're done. All right, so we do our test statistic, our p-value, and a normal curve with shading. Make sure that you have those 3 components. I mean, you have to do your p-hat in order to calculate your test statistic. Okay. And then the conclusion. And we will show you sort of how to do this with your calculator in a future example. So hang on with that. All right, conclusion. We're going to compare our p-value to our alpha. In this case, it's less. Therefore, we are going to reject the null hypothesis. And so 2 components there. And then the third is there is convincing evidence that, and now we're going to say this alternative hypothesis in context, in words and in the context of the problem. So there is convincing evidence that more than 12% of Montclair High School students plan to opt out of the exam. All right, so let's think about how we would do this in our calculator. So how would we do this calculation in our calculators? All right, so now what we do is we hit, hang on, let me get my calculator out. That is the stat button. So we hit stat. And then we go over, we haven't done this yet. We're going to go over to tests. All right, and so there's a whole huge list of tests. And so right now, there's a slight disconnect between what our textbook and the College Board calls its procedures. So this procedure here, a 1 sample Z test for proportion, and what the TI instrument, Texas Instrument people call these. So this one sample Z test for proportion, the Texas Instrument people call it a one proportion Z test. You have to be very specific and very careful about which one you pick out, because there's a lot of different tests here. So we want to choose that one. And then once we choose that, this screen pops up. And so it's asking us for some stuff. It's asking us for the hypothesized p-value, 12%. It asks us not for p hat, but for x, the number of successes in our sample, and the sample size. And then it also says, it asks for the alternative hypothesis. So the proportion, and then we say greater, not equal to, less than, or greater than. All right, so that agrees with what we had in our alternative hypothesis. So the p-value, or the proportion, and then we have three options, not equal to, the less than, or the greater than p naught, which would be the 0.12. So we want the p-value greater than 0.12. So we're choosing that last one. Okay. So that's how we decide which of those things we choose. Let me erase that so that we can kind of see that better. So the alternative is that p is greater than 12%. And so that's why we chose that last one. Okay. Then what we do is we hit calculate. And so a lot of things are happening there. So if we hit calculate, we get the Z statistic and the p-value. All right, be careful, because it also gives us a p hat. We don't want that. We want, when we do our do, if we're using our calculators, great, more power to you, but you still have to give me the Z statistic, the p-value, and a normal curve with shading. So those three things still have to be in your do. All right, now you could also, if you wanted to, instead of hitting calculate, you could hit the draw, select draw, and hit enter, and it will actually draw you the shaded region on the normal curve, just like we have up here. Okay, so it will draw the normal curve for you as well. You have to go run through it again and then select the draw to get that. All right. All right, let's talk about a two-sided test now. All right, so a two-sided test, the alternative, the null hypothesis looks the same, but the alternative hypothesis is that p is not going to be equal to that particular value. All right, p-value in such a test is the probability of getting a sample proportion as far or further away from the p naught, but in either direction. All right. So notice that we have to look at the areas for both sides, right, into both tails. So let's first do an example, and we're going to do that by hand, and then we'll do it in your calculator as well. All right. So your friend Bob, a CPA, claims that 65% of his clients get an IRS tax refund. Now, I know Bob, and he's a habitual liar, so I just think he's making stuff up. He's not telling the truth. I don't think he's bragging or he's being modest. I just think he makes stuff up when he doesn't know. So that 65 is probably just wrong, but I'm not sure which direction. So write your state, knowing that we just think he's just not telling the truth. All right, so we're going to say as our alternative that it's just not equal to 65. We don't have an indication that it's higher or lower. We just think it's not equal to. All right, so an alpha of 0.05. And again, if they don't tell us the alpha level, the default is 0.05, so 5% for our alpha if they don't tell us. All right, and then we say what the P is. The P that we used in the null and alternative hypothesis is the true proportion of clients who got a refund. All right, the plan now. pause the video and write out your plan and your conditions. All right, if the conditions are met, we're going to run a one sample z-test for P. The sample, his 200 returns were randomly sampled. We know that he's got 3,000 clients, so 200 is okay. And we checked the large count. N times P naught was on 130. N times 1 minus P naught is 200. So we know the sampling distribution of P hat is approximately normal, which is going to allow us to calculate our test statistic, our Z statistic. All right, so do your do. All right, so we do our P hat, we do our Z score, and then we go, if we wanted to, we could go now to our Z score table, or we could use a calculator, and we could find our P value. Now we did this by hand, but we know that it's a two-sided test from the alternative up above. So if we do it by hand, we have to make sure that we double our P value, because this, if we're looking at the test, the Z-score table, that's giving us the area just in the one tail. We don't know what direction, right? Ours was like, well, the probability that we're far enough, we're into the tail or further into the tail than we are, but in both directions. So the P value is larger. All right, so that's why we have to double the P value. All right, try doing this in your calculator. If you do it in your calculator, you would have chosen the not equal to as your alternative, and it doubles it for you. So you would, if you're getting your P value from your calculator from the one prop Z test, then you don't have to double it if you picked the two-sided test, the not equal to. All right, conclusion. Our p-value is greater than, or 0.075 is greater than 0.05. So we failed to reject the null hypothesis. And then we say, in terms of the alternative, that there is not convincing evidence that the true proportion of Bob's clients who get a tax return is not equal to 65%. Okay, there's a lot of nots in there. We do not have convincing evidence, right? It's almost like an English teacher would be like, oh, wait, you have a double negative here. You should get rid of that. But if I got rid of those two, if I got rid of that not and this not, then what is that final part saying? It's saying that there is convincing evidence that the true proportion is equal to 65%. And so that's different. That's not saying we don't have convincing evidence of HA. That's saying we do have convincing evidence of H naught. And we don't want to say that. We don't want to say like we support H naught. We just don't have enough evidence to reject it. So we failed to reject it. And as a result, we have to just say there is not convincing evidence that it is not equal. All right, so it kind of, an English teacher would get mad because they have a double negative, but we have to say we do not have convincing evidence of HA, and HA is not equal to. Okay, so it's subtle, but there's a big difference. You'll lose a point if you just got rid of both those knots, because you're not saying, you'd be saying, if you got rid of those, you'd be saying that there is convincing evidence of H naught. We want to say that there's not convincing evidence of HA. Okay, so you have some homework, and that homework has two four-step problems. So number 41 and number 45 are 4 steps. Make sure, if you want to get full credit on your homework, that you're doing those 2 problems using your 4 steps.